have Larry Hastings, who is going to talk with you about stepping through CPython.
That was the wrong thing. Boom! There we go. All right. Ladies and gentlemen, boys and girls, children of all ages, it's time for stepping through CPython. My name is Larry Hastings. This is PyCon 2012. You'll note there is no introduction to this talk. That's because this is an extreme talk. However, if there were to be an introduction, not that there is, I would say that this talk is an architectural sightseeing tour of the CPython source tree. The goal here to be to familiarize all of you with the CPython implementation enough that you can become core developers. So this isn't going to tell you everything you need to know. There's a lot you need to know. But this is to sort of give you the lay of the land so that you can take the next steps on your own, reading online documentation and asking informed questions. Now this is about Python, specifically about Python 3.2.2, because as core developers, we're really not interested in the 2 series anymore. It's about Python, it is in C. I'm going to be talking about the C implementation of Python. We're going to talk about a Python program, but we're not going to talk about how Python works. I'm not going to tell you anything about writing Python. I assume that you know Python, I assume you know C, and in fact I'm sort of hoping you know a little bit about machine implementations because there's some stuff in here, so there's a virtual machine inside of Python. So now the name of the talk is Stepping Through CPython. I don't have time, so it's not really going to be stepping so much as running. The artifice of the talk is, however, that I'm running under GDB. So let's start, however, with a high-level directory organization of the CPython source tree. These are the kind of the less interesting ones. Doc is in doc. The Python grammar is in grammar. There are 2 directories for building on specific platforms, PC, build, and Mac. And then there's just a whole bunch of crap inside of MISC and tools. There's Python scripts, there's C programs, there's a lot of documentation. It's sort of a grab bag of stuff. The 5 directories that are really interesting include, lib, modules, objects, and Python. And as a core developer, that's where you're going to spend most of your time. Include has all of the visible, the public include files for Python. There are include files in other directories, but those are going to be private. The include directory is actually what's installed when you install the Python interpreter. Lib is the Python portion of the Python standard library. It's almost all .py files. Modules is C implementations of Python modules, so that's the C portion of the Python library. And objects is where the objects are implemented. That's going to be tuples and sets and lists and floats and all of those things. And actually there are a bunch of objects that are used just strictly internally by the Python interpreter that you'll see in there as well. And the Python directory theoretically represents Python itself. That's where the importer is, that's where the parser is, that's where a bunch of the bookkeeping stuff is. And I will say that modules and objects in Python also, again, just have a bunch of miscellaneous crap in them, and then we're going to see that in a minute. The Python, the code itself embodies pragmatic over purity in a lot of places. So this is the program that we're going to be running under Python as we're stepping through it. It's only 8 lines. It is deliberately simple, but again, trying to hit a sort of a lot of high points. And we're not going to talk about what this program does so much as break down how it is run inside of Python. So down the rabbit hole we go. We run GDB on Python 3. We set a breakpoint on main, and we start. Immediately we hit main, and we're going to talk about this first line here. But first, let's talk about main. Main lives in module/python.c. It doesn't do a whole lot. It makes a couple of copies of argv. It sets the locale. Under FreeBSD, it sets some floating point control bits or something. And then it calls into PI_main, which is the main Python main for all platforms. And I want to tell you, by the way, I'm not going to go into this much detail over everything, but I did want to stop in main because this is the first place where we hit memory management. Literally the first line of code that's executed in kind of Python is allocating memory, and it's calling one of the 2 families of memory management in Python. The 2 families are called PyMem and PyObjectMemory, the PyObjectMemory family of functions. When I talk about these families of functions, I mean that's the Python term for them. For these families, there are always triplets of functions. There's always malloc, realloc, and free. Just to save time, I'm only ever going to mention the malloc forms, but there's always all 3. So the last thing I'll say before the next slide is, in general, please don't call malloc inside of C, inside of Python. It's not the end of the world, but there are some wonderful things that you get from using these functions. There are some calls inside of malloc, and it's not the end of the world. People haven't cleaned them up. But in general, it's better if you use PyMem or PyObjectMemory. So the first family I'm going to talk about right now, the second one I'm saving until much later, PyMem functions. These live in include PyMem.h and in objects object.c. They're just sort of stuck in object.c because the implementation is really small, because all they are is a thin veneer over Malloc. There's a C function called PyMem_Malloc, which just calls Malloc for you. And then there's a preprocessor defined PyMem_Malloc all caps, and that calls Malloc, unless there is a preprocessor defined turn on called PyMalloc_debug. PyMalloc, there's really nothing in Python called PyMalloc. I don't know why they named it this, but there you are. So PyMalloc_debug activates a whole different subsystem for allocating memory. The function called here is PyMem_debug_Malloc. The debug malloc is like a mini Valgrind built into Python. It's really cool. Whenever you allocate memory, it allocates guard bytes on either side, and it keeps track of all the allocations that have ever existed, so it can tell you what stuff's in use right now. If you have memory allocation problems in Python, you turn this on and you start getting information right away. You can also turn all of this stuff off if you want to use real Valgrind, because those are just going to step on each other's toes. So, dispensing with memory allocation for now, let's set our second breakpoint in PyMain, and we jump to it almost immediately. So PyMain lives in module/main.c, and I really want to draw your attention to this. Main is in python.c, Python main is in main.c. Both are in modules, even though neither of them implements a module. PyMain does 5 things by my count. It handles command line arguments, it handles reading environment variables, and both of these things set some flags internally for that the Python interpreter reacts to. It sets up the flow control stuff on standard in, standard out, standard error, the way that Python wants it. It calls PyInitialize, which initializes all of the Python internal modules and internal types that are used by the interpreter. So that's a major part of bootstrapping, and we'll address that a little bit later. And finally, it calls whatever thing you actually asked the Python interpreter to do for you. It runs the script, or it runs the module, or it runs the command. So we're going to set our third breakpoint in PyObject_new, and hit it almost immediately. And then for the artifice of my talk running under GDB, we're going to clear that breakpoint, because if you left that set, you would hit it over and over and over and over and over. Everything in Python is a PyObject, and I mean just almost everything. It's a fundamental structure inside of the Python interpreter. In C++, we would actually inherit from this PyObject structure, but we're C, so we don't have inheritance, so it's just that the Python interpreter requires you to declare a PyType object, or excuse me, a PyObject at the head of any object that you're going to pass into the Python interpreter. So PyObject really is everything. It's not just dicts and lists and tuples and sets. It's also type objects. It's strings, integers, and floats. It's stack frames. It's a lot of internal runtime details of the Python interpreter are implemented as PyObjects. So this thing better be small, and it is. Oh, I forgot to mention it's an object.c and object.h. So here's the structure. This is it for a PyObject. This is at the beginning of every object that's running inside of the Python interpreter. And I'm going to break this thing down for you. So the first thing is called head extra. You'll notice there's no semicolon at the end. It's not actually a real thing. It's a preprocessor macro. Under normal conditions, it actually evaporates into nothing. The only thing this is used for is if you want to watch all the references inside of Python, you can turn on something a preprocessor defined called PyTraceRefs, which adds 2 fields here, previous and next pointers that are used for a global linked list of all objects in the Python interpreter. Which means that there are 2 things. First of all, under normal conditions, there is no central directory of all Python objects, which means that the Python interpreter has no idea what objects exist. You could introduce new objects at any time that it's never seen before. There could be millions of objects and it has no idea where they are, just floating off in the heap somewhere. It also means that if you want to turn this on, this is touching the memory representation of every object in the Python interpreter, which means that you have to recompile everything. Not only recompile Python, but you have to recompile all of your extension types, because you're changing what objects are. So the second thing in this structure is always there. It's a reference count. It's of type pi size s size t, which is a signed, relatively big native integer. This is an integer number of references that exist to this object. When it reaches 0, we call the deallocator. The deallocator lives in this third member, which is obtype, which is a struct type object. You generally use the typedef for that, which is called PyType object. And let's talk about the type object. So I do want to point out, by the way, in a legal object, obtype is never, ever null. All objects in the Python interpreter have this structure at the head, and they all have a valid pointer to a valid type object in that member right there. And so everybody's using PyType objects as well. So here's the PyType object. You'll notice that it is enormous. There are 52 members inside of it, and then we can add some bonus members later. It used to be that when you wanted to declare an object that was going to live inside the Python interpreter, you would copy and paste a static instance of this structure around, which was a real pain in the ass. You had to sort of find one that was kind of similar to what you wanted to do, and then change just the little details that you wanted different. PEP 384 adds what's called the stable API, which allows you to construct these dynamically with function calls, and it really is much better. So I'm hoping that people who add new extension types in the future always use the stable API. So this has 52 members, as I mentioned. Some of these are function pointers that implement things like dealloc, or also repr, hash, rich compare, getattr, and setattr. Most of the details here are actually data. There's going to be integers. There's going to be pointers to data. And then 4 of these are actually pointers to structures that contain more functions, because we didn't want to fit them all in here. So those add a potential another 50 function pointers inside. These 4 optional structures are representing what I would call the protocols. And actually, I guess everybody would call them the protocols, because they're the protocols. The protocols are implemented in abstract.h and objects abstract.c. And this is something that you're actually familiar with as Python programmers, because it's reflected very strongly in the Python interpreter as well. So a protocol is really sort of another name for an abstract base class. This is a way of treating a Python object as an instance of a specific kind of thing. And there are 5 protocols, and you're going to say, oh, that's what those are. So first there's the object protocol. Every object is a member of the object protocol, obviously. But if you want to be a buffer, then you add a struct called TP_as_buffer, and that has all the functions that are things that are exposed by the buffer protocol. Similarly for number, TP_as_number, and that's where things like multiply and divide would be. Similarly for mapping, that's where getItem would be. And you're in your head, you're saying, oh yeah, that's where those dunder, getItem, and all those things, that's how all of these are reflected in the C interpreter. It's this pointer to this extra structure that contains function pointers. The last one, sequence, and you see that a whole lot. And in fact, sequence is so important that there's actually a little bit of a, hack is too strong a word, but there's what's called the fast sequence. Fast sequence, if you're doing an iteration over a Python object in C, you really should call fast sequence instead of doing the normal sequence stuff. Using the protocols is a little on the slow side because it's very general code. And 90% of the time inside of Python, when you're iterating something, it's really a real list or a real dict object, the real ones that are implemented in C. And it's very easy to pull the objects out of the real list or the real list or real tuple. And so what the fast sequence code does is it says, oh, this is a real list or it's a real tuple. I know how to pull the thing straight out of that. If it's anything else, but it exposes the sequence protocol, then it actually does it the nice, slow, general way, and actually allocates a list and populates the list with the elements that it iterated over, and then it iterates over the list using the fast way, and then it drops the list for you. So anyway, if you're iterating inside of C, you should use fast sequence. So let's talk a little bit about reference counting in Python. Again, all objects in Python are reference counted. There are 5 macros here. The base 2 are incref and decref. Incref ups the reference count, decref drops it, and if the reference count reaches 0, then we deallocate the object. There are the safe versions of these functions calledxincref and xdecref, which just does a null check before, and if it's null, then it doesn't do anything. Otherwise, it calls incref and decref for you. And then there's PyClear, which very cleverly makes a copy of the pointer first and then calls xdecref, which means that if you have a field inside of a structure and you're deallocating it and it's kind of a circular, you're sort of going all around and you could be dropping it and you could be reentrantly deallocating and getting around back to this thing again, then we've set it to null first so that you don't actually re-enter and start the whole cycle again. So PyClear you use for things that are members of other structures that you might be reentrantly reaching. In general, I think most people call PyIncref because generally when you have a reference, it's not going to be null. You already know this legit. And then people call PyXDecref just to be safe, and PyClear when that's appropriate. So now it's time actually to talk about the PyObject memory allocator. This is, again, the other family of memory allocation functions in CPython. These live in include objimple.h and objects obmalloc.c. You only get this if the preprocessor defined with PyMalloc is turned on, and again, there's nothing specifically called PyMalloc, but that's what they called it. There's the main C function you're going to use here is PyObject_Malloc, which is the implementation of a custom small block allocator for Python. And I'm going to go into a lot of detail about how that works because it's really neat. However, if you have PyMalloc_debug turned on, again, that mysterious PyMalloc debug, then this calls into PyObject_debugMalloc, which again is talking to our friend, the mini Valgrind inside. There's also a preprocessor defined called PyObject_Malloc all caps, which does just what you would want it to do. It normally calls PyObject_Malloc. If you have PyMalloc debug turned on, it calls that one. And if you don't have with PyMalloc turned off, then it calls into PyMemMalloc, which is the preprocessor macro over Malloc. So let's talk about the small block allocator. I'm going to kind of start at one end and work my way through to the other end rather than going top down. So just sort of follow along. We start with the arena object. And we have a linked list of these arena objects, which themselves have pointers to a big block of memory that we allocate from Malloc. And when I say big, it's 256K. I think it's tunable, and I don't think anybody ever touches it. So we have a linked list of these arena object structs, and each of them points to arenas. Inside of the arena, what we do, we go forward. We hope our slides go forward. There we go. It's just a little slow. So inside of that is we strip it into 4K blocks that are actually rounded to the 4K address. And what's interesting is talking about what's inside of that 4K block, so we're going to sort of zoom in on it. The very first thing in the 4K block is what's called a struct pool header. So this 4K block is now referred to as a pool. The pool header knows how big of all the allocations inside of this pool are going to be, and it has a free list pointer. The Python small block allocator doles out memory in 8-byte increments. So you'd get 8 bytes, 16 bytes, 24, 32, 40, 48, on and on, up to a couple hundred bytes. So what we do is we allocate the pool header at the very front of the block, of the pool, pardon me, and then we carve up the rest of the memory inside of that 4K block into just exactly that size. There's actually no per allocation overhead in the small block allocator, which is why it's nice and efficient. So we pre-populate a free list with all of the blocks inside of the pool, and then we start handing out memory from it. So under normal use, it's going to kind of look something like this. There's going to be this free list pointer inside of the pool header. It's going to point to some random block somewhere in the middle, and those are going to point to the next and next and next until you run out of blocks. The ones that are allocated, we actually don't have any reference to. Again, there is no per allocation overhead. When you call free and pass one of these things in, the Python small block allocator figures out whether it's real Malloc memory or whether it's small block allocated memory by saying, is it inside of one of the arenas? Oh, it is. Okay, then we can take its address, shave off the bottom couple of bits, and that'll give us the head of the 4K block, and that's the pointer to the struct pool header. And so now we can figure out what the disposition of this memory is. But because there is no per block allocation data, that means that we have no record keeping on the block, which means that a double free will absolutely kill you. If you double free something, it gets put on this free list twice, and then something terrible is going to happen. You're going to allocate it, and then the free list pointer is going to get overwritten, you're going to crash, something terrible will happen, which is why Python has a mini Valgrind built into it. So let's talk about how you organize the pools. The struct pool headers live in these circularly linked lists, doubly linked. Boy, that's hard to say on stage. This ring of struct pool headers, this is specifically for pool headers that are partially in use. If it's totally empty, then it's living on a free list of pool headers that are ready to be used for somebody. If it's totally full, it actually gets disconnected from this ring, and it's just floating off in the heap somewhere. Again, Python is not tracking something that's completely in use. So these are only for things that are partially in use, and therefore they are linked to from a static array of these structures called used pools. And this is actually the first thing that the small block allocator hits. So this is really kind of where I should have started, and it's at the end, but that's how we got here. So this is an array of actually stubs of the heads of these circularly linked lists. And if it's populated, then that means that there is some memory available in it. And so the small block allocator, what it does is it takes the allocation you asked for, rounds it up to the next 8 bytes, shifts it right a little bit, or right for you guys, and uses that as an index into this array, and then looks to see if there is anybody in the circularly linked list besides the header that's in the pools. And if there is, then it must have free memory. If there isn't, then it goes and tries to get a new pool. If there are no pools available, it allocates a new arena. If there are no arenas available, try to allocate a new one. Malloc fails, then you're out of memory and your world ends. And this whole design, by the way, is why Python seems to never give memory back to the operating system. If you have one block allocated inside of one pool, inside of an arena, then we have to keep the whole arena alive. So arenas just tend to stay around forever. So you allocate a whole bunch of memory and you give all of it back, but there's a little bit of fragmentation, now all the arenas are staying alive, and the Python process stays as big as it was. There was a little bit of jiggery-pokery in 2.5 to try and change the allocation pattern and fix that a little bit, but it kind of doesn't work. So it's time for our last breakpoint. We're going to spend a lot of time on this. This is PIeval _eval frame EX. And again, with the artifice of my talk, I'm going to clear the breakpoint because otherwise we would be hitting it constantly. So PIeval _eval frame EX lives in Python /ceval.c. And this is what I would refer to as the big eval loop. And it is big. This single function is 2,300 lines. It's the biggest single function in the Python source tree. PIeval _eval frame EX, which I'm getting a little tired of saying, is an implementation of a stack-based virtual machine that implements the machine that runs Python bytecodes. This is the beating heart of CPython. And it's stack-based in terms of it has a data stack. The return stack is actually sort of implicit in the Python C runtime because whenever you call a Python function, that's mirrored in the C stack, and so that's why you can blow the stack with having a really deep recursive set of calls. That's the thing that Stackless kind of was set out to change. So let's talk about the phrase virtual machine. It really is a virtual machine. I really like this analogy because it's really apt. It is both virtual and a machine. It's virtual in that it doesn't exist in the real world. It just exists as a software abstraction inside the box near your feet that gets warm. And it is a machine in that it has all of the attributes in the machine. And so when I say machine, I mean computer. So it really does have all the attributes that a computer would have. It has registers, for instance. Here is all of the local variables declared at the top of PIeval _eval frame EX. You'll notice they all say register. That's just a pun, really. But these are, like there's a stack pointer, and there are general worker registers. There's a whole bunch of those that are just there for people implementing bytecodes. There's a bunch of stuff that's specific to Python, of course, that a normal computer wouldn't have. So we have registers, we also have opcodes. These all live in include/opcode.h, and there are 80 of them. Actually, I couldn't fit all of them on this slide. So let's talk about how you would implement a virtual machine if you were going to write one. If you want to write cross-platform portable C, the standard way to do it was with what I'd call a switch loop. You have a big for statement. Inside of that, you have a switch, and you have a pointer to each of the opcodes. And you dereference it, and you auto-increment, and then you switch on that opcode, and you jump to whatever is going to do it. Like binary add or binary subtract, you have the implementation that's going to do the work for that instruction right there. And that's how Python was implemented for a long time. But a couple of years ago, somebody figured out something to make Python go a little faster. That kind of complicated our lives a little bit. We're going to see it in the code in a minute. So this was an issue on the Python bug tracker called faster opcode dispatch on GCC. It was issue number 4753. And this is using two GCC extensions to C called labels as values and computed gotos. They're actually available in GCC, Intel's ICC, and Sun Studio C. The one place where we don't have them, where we really want them, is Microsoft Visual Studio. So on Windows, we can't use this anymore. So it's actually switchable at compile time, whether you use this faster opcode dispatch stuff that I'm going to talk about, or whether you use this traditional switch statement inside of a for loop. The Python interpreter still supports both. So how this works, you have a new operator in C, double ampersand followed by a name of a label. That's the unary double ampersand operator, which never existed before. And this is an expression of type void star. So you can take that value and assign it to a void star pointer. And then you can do the second thing, which is the computed goto. On a goto statement, normally all you could have there was a label. Labels are the things that you jump to with a goto statement. But now you can also dereference a void pointer, which always makes me feel a little funny inside. And you jump straight from that goto to the label, whatever it is. So we've just jumped past our exit, and we're going to call printf here. So that's how we would implement the virtual machine in Python. That's how it's implemented right now. So now it's time to actually talk about our program again. You remember this? So this is my 8-line program. I'm going to break this down into the bytecodes that Python compiled it into and talk about what those bytecodes do. So let's start with the first line, obviously, import sys. This turns into 4 instructions. Now let's talk about the formatting here. This first column with the 1 in bold, that's the line number. I should say this output here, this is from the dis module that's built into Python. So this is Python, a bytecode disassembly. So 1 is the line number it came from. The next column is the bytecode offset inside of the code object where we find the bytecodes. Next we have the representation of that bytecode from opcode.h. And then if the bytecode takes an argument, then we have a 16-bit integer, which means different things to different opcodes, and I'll talk about what those are. All of these bytecodes happen to take an argument, and so they're all 3 bytes long. You can see that 0369. So load const, what that does is it loads a value, a static value, from a constants table that's associated with the code object and pushes it onto the data stack. The constants are referenced from an array, and that's 0-based, and so 0 happens to be 0 and 1 happens to be none. So we just push those two things on the stack. Then we call a bytecode called import name. That takes an argument that is an index into a different table called names, which are all strings. And 0 in this case is sys. So import name actually doesn't push it, it just uses it directly. And what import name does is it calls dunder import, or it actually calls the C implementation of dunder import, which is a different function. So this dunder import actually takes 5 parameters. So we've seen 3 of them here, 0, 1, and the sys string. The sys is the name of the module. The none represents, God, this is in my notes and it's not scrolling down. There we go. So dunder import takes 5 parameters: name, locals, globals, from list, and level. Name is this sys. Locals and globals, it just uses the current scopes that are already defined. From list is for the form of import where you say from whatever import A, B, C. That's the list of names over there. We don't have that. We just used import sys, and so it's none. And level reflects whether it's an absolute or relative import, or you can have a negative number that's this old school mixed thing, and let's not talk about that. So import name pushes its result on the stack, whatever thing that it is loaded. So that's going to be a module object in this case. And then we store it, and again we store it. Store name takes the parameter, which is an index into the names array, which is sys. That's what actually binds the module to the name sys. So let's talk about what happens inside of import name. In this case, not a whole lot. There are a whole bunch of modules that are preloaded as part of Python bootstrapping itself. And you can actually see the list yourself pretty easily. Just run the Python interpreter, import sys, and print out sys.modules.keys. Sys.modules is a dict mapping string names to modules that are already cached inside of the Python interpreter. And if you do this, you're going to see 53 of them. A Python interpreter has done a lot of work before it actually gets around to running your code, the little scamp. Sys is, I think, about the first one, but there are a whole bunch here. A lot of these are implemented in C, but some of them are actually implemented in Python. So the Python interpreter has actually started running Python before it ever got around to running your Python. And since sys has already been loaded, it's already sitting in sys.modules. The way that import works is the first thing it does is it looks in sys.modules to see if there's an entry there. If it does, it just returns whatever it is. Which, by the way, means that if you stick stuff in sys.modules and you say import whatever, you'll get that, whatever it is. It doesn't have to be a module. You can do all sorts of kooky things with that. So let's talk just for a minute about modules in C. All the modules that are implemented inside of CPython, again, they're in the modules directory. They tend to end in modules.c. They're all initialized inside of PyInitialize, which is in Python run.c. And I don't know if this is shocking, but I'm just not going to spend a whole lot of time talking about how to implement extension modules, A, because I have no time, and B, because there are a lot of resources about this. There's a built-in document in the Python documentation called Extending and Embedding the Python Interpreter. It talks all about writing extension types and modules. And also, Ned Batchelder gave a really excellent talk a couple of years ago at PyCon called A Whirlwind Excursion Through CPython Extensions. As a core developer, if you're working in C, most of the time you're working on a type or a module, and so this is where you're going to spend all of your time. And I'm not talking about it, which is kind of a shame, but this is so that you can understand the context in which these objects exist. So let's go back to our bytecode. We finished up with import sys, so let's move on to the next one, which is import color sys. This is almost exactly the same. The only difference is that we're importing a different module, but under the hood, a lot of different things are going to happen. I picked color sys because it's implemented in pure Python and it's not bootstrapped by the interpreter. It's actually to do color space conversions like RGB into HSV and that sort of thing. So here's libcolorsys.py, and the Python interpreter at this point isn't going to read it. because we've already pre-cached a tokenized version of it called pycache_colorsys.pyc. The actual file name is a little more involved because of what happens in the pycache directory. But this is a whole big blob of binary data. I'm not expecting you to read this either. This is just soup for, this is illustrative purposes. But let's talk about PYC files. PYC files are Python's objects that have been serialized straight to disk. The serialization is using what's called Marshall. This is a serialization format built into Python that's used almost exclusively for this. In general, you shouldn't use it for your own stuff because it tends to change whenever Python changes. If you have, you add or remove things from Python types, the Marshall format changes. And when the Marshall format changes, they just change it. They don't worry about backwards compatibility at all. So you should use pickle if you want a binary serialization format in Python. But Marshall is used here. A marshalled.pyc file contains 3 Python serialized objects. The first 8 bytes of the file are 2 serialized 4-byte integers. The rest of the file is all a single serialized Python code object. So the first 4 bytes are a 4-byte integer that's referred to as the magic tag. This is documented pretty well in a big comment inside of Python import.c. This is effectively the serial number for the format of the rest of the file. And again, anytime that the format of a PYC file changes, we change this number. So it's always a unique serial number. And again, we change it all the time. There have been 45 different magic tags inside of Python to date. And if you count, there are nowhere near 45 different releases. So we changed them during the alphas and betas as well. This particular flag, this particular magic tag is currently 3180, and then that's ANDed with a couple of extra bytes that live in the top. So that when it's written out to disk, the current tag is 0C, 6C, 10, and 13, which turns into form feed, lowercase l, carriage return, and line feed, which means that if you cat it to the screen, you get a new line, which is great because I'm not sure. The next 4 bytes are the M time, the modification time of the PY file that this PYC file represents. So that's what happens when we import this is Python says, oh, there's a PY file, there's also a matching PYC file, let's read that, read the M time, call stat on this, and if they match, then the PYC file is nice and fresh and we just use that directly and it's a lot faster. If they don't match, then we throw this away, we retokenize this, we write out a new PYC file, and then we proceed from there. Whatever the result is, once we've loaded it, we cache it in sys.modules, and then that gets returned back to the user. The mechanism is the same, it's just we had to do a lot more work that time for colorsys. So let's talk about our def statement. You'll notice def foo return a plus b. We don't actually see the plus statement in here. The contents of the foo function have already been tokenized, and they're already existing in one of these code objects that's stored in the constants table. So all we do when we say def at runtime is we load the constant that represents the code of the function. We call this, this thing called make function. That's an opcode that turns a code object into an actual Python callable. The argument to make function is an integer. It's actually 2 integers that have been bit shifted together that represent how many positional arguments and how many name value pair arguments are going to be passed into this function. The result of make function, it pushes a callable object onto the stack, and then we call store name again, and we just store it just like we stored the imports. So we don't see the code for foo here. I'm going to return back to it, but we're going to go through the rest of the bytecodes first. So our next line is our nested function call. We call print on the result of calling foo, which we're passing in 17 and 25. So load name is loading, that's the opposite of store name. We're loading variables and pushing their values onto the stack. So we call load name print, and that pushes the callable object on the stack. Then we call load name foo, which pushes that callable onto the stack. Now we load the 2 constants, 17 and 25, and we call function. Call function, the argument there, it's another one of these bit fields that mask together. It's saying, again, how many positional and name arguments to expect. This doesn't take any name arguments, so it's just 2, which is the number of positional arguments. If there were name arguments, those are actually passed on the stack as value followed by a string that is the name of the argument. So this call function 2, that's going to pop the top 2 things off the stack, build them into a tuple, because that's how Python actually passes arguments internally, and then call the TP call inside of the type object for the code object that's sitting at the top of the stack, passing in that tuple. And that's where the actual functionality, that's where the magic happens. That is going to return a value to the Python interpreter, and that value is then pushed onto the stack. So after the end of this call function 2, the result of foo is sitting at the top of the stack. Underneath it is the code object for print. And so now we just say print call function 1, which pops the top value off the stack, which is the result of foo. Build that into a tuple, pass it into the code object that's now at the top of the stack, which is print, and we print. And this is going to print the result. The next instruction is pop top. Every time you call a function in Python, it returns a result. If you're not interested in the result, as we are not interested in the return value of print here, we just throw it away. So pop top just pops the top value off the stack and ignores it, and just dereferences it. So next, we bind a class. I'm kind of running out of time, so I'm not going to talk about this too much, but it's very similar to binding a function. We just, it's a little bit more involved because there's a little bit more work to do. You'll see that there's a make function, a load constant call function that's calling the code inside of the class. We don't have any here, but if there were, assignments and things like that, more def calls, all that stuff, that's where it happens right there. And the result of the call function there is the module of the class object pushed to the top of the stack. And again, we call store name to bind that to capital C. So the last line of my bytecode here is C equals capital C. And it looks very similar. We're loading the name, we're calling the function, because classes are just callable objects in C. And we're storing the result in lowercase c. And I really want to drive home to you that the mechanism for this assignment, C equals, the same mechanism is used for binding class C and used for binding def foo and used for binding imports. They all call store name. There's nothing fundamentally different about sys versus C versus foo versus capital C. Those are just attributes of the current module, and they contain wildly different values, but the attribute access is all fundamentally the same. So let's circle on back and talk about the bytecode for foo, because it's a little bit different than what we've seen before. Load fast is something we haven't seen yet. This pushes a value from what's called fast local storage onto the stack, and the argument there is an index into the fast locals array. Fast locals were something that sped up functions a whole bunch in Python. The fast locals, when you call a function in Python, it gets a fresh fast locals array every time, and it's pre-initialized to null, not none, but null, which in Python represents uninitialized value. The fast locals array, that's where we store arguments to the function, and that's where all of the locals for the function are stored. So this was a lot faster than doing name lookups for all locals and arguments in a function, and sped up Python quite a bit. It was done very early on. It's been in Python forever. And there's a symmetric store fast as well. Binary add takes the top two things off the stack, whatever they are, and attempts to add them together using the number protocol. It pushes the result on the stack. And then return value is going to return the result of that back to the caller, whoever that is. And I wanted to break down one of these opcodes for you. I was kind of use binary add, but binary add is a little on the pragmatic side. So I'm going to use something a little simpler, which is binary multiply. So this is literally the implementation of binary multiply in Python 3.2.2, and I'm going to go step by step through it, thus fulfilling the prophecy of stepping through CPython. So the first line here, target binary multiply, this is a preprocessor macro just to hide the difference between whether we're traditional switch statement or labels as values, but this is declaring this is the top of the implementation of binary multiply. Underneath it, we have pop and top. These are local preprocessor defines that deal with the data stack. Pop pops the top value off the stack and returns it. Top just makes a copy of the top value of the stack. Conceptually, binary multiply again pops the two values off the stack, adds them together, and pushes the result. But it's actually cheaper to not bother with the redundant stack move. So we just pop the top one, copy the other one, add them together, and overwrite the top. W, V, and X, by the way, those are some of those local registers inside of PIeval _ eval frame EX. They exist just to be workers, general purpose registers for code exactly like this. So the next line, PINumberMultiply, that's a member of the protocol, of the number protocol. PINumberMultiply is going to attempt to multiply those two things together, and we store the result in X. And so actually, let's step into PINumberMultiply and see how it actually works. So here's PINumberMultiply. It's kind of hard to see maybe because it's a little small, but that is the entire function. The first line is calling something called binary op1. That's a local worker function in this file that attempts to use the number protocol, it looks in the type object if it has a TP as number, and if the TP as number has an entry in this particular slot, which is the NB multiply slot, then it attempts to call it. It calls each one to see if this one will accept the other one or if the other one will accept the first one. If it can get a result out of that, then we're happy and we return it. If that doesn't work, then when PINumberMultiply, it says, okay, maybe one of them is a sequence and the other one's a number. Because in Python, you multiply a sequence by a number, you get a new sequence which has number copies of that sequence sitting in it. And so it tries again using the sequence protocol and the number protocol to say, are you a sequence and are you a number? And if so, can we get you guys to get together? And if so, it returns the result of that. If that doesn't work, then we give up. We call another local worker function called binup_type_error, which creates a new type error object and raises it internally and returns null, which again represents invalid value. Whatever this returns is going to get pushed back into X, and then we sort of go on with our lives for a minute. We drop our references to V and W. I'll point out, by the way, these aren't the safe versions because we're guaranteed at this point that V and W are always legal. And now that we're done with V and W, we're going to set the top of the stack to be X. And we're actually done with our multiply. And now it's time to go on to the next instruction. So if X is not null, we call something called dispatch, and otherwise we break. In the old school big eval loop form, which is just the for loop over the switch statement, I think dispatch doesn't do a whole lot. I don't remember, I didn't look. But under the labels as values version, it has a lot of complicated code in it. It checks an internal variable called eval breaker using a nice clean atomic read operation. And if it's 0, then we use a computed goto to jump to the next instruction, whatever it is. Otherwise, this just exits. And if it exits, then it hits the break. And if we hit the break, then we exit out of the whole eval loop. And there's a whole bunch of housekeeping at the bottom that does things like, oh, is it time to give the thread back to somebody else because it's time to let another thread run? Oh, has somebody raised an exception? Do we need to start unrolling the stack and life is coming to a stop? So if PINumberMultiply failed, then X is going to be null, and we're going to break out and deal with the exception that's been raised. And that's actually kind of it. I'm surprised at how fast I went with all this. We're done with, this is not incrementing, so we're done with our process. We continue and we hit the end. We produce our output. Foo printed 42, wasn't that clever? And I'm actually done. And I actually have some time for questions. Wow, look at that.
Okay, we do have a couple minutes for questions before lunch.
Before lunch.
If you have questions, come up to the mic, please.
So in Ruby, in the core interpreter, to fill out all those slots and things like that, you just say add function plus sign, the function in C. Why is Python so complicated with the structs and whatnot?
Ladies and gentlemen, this is Jack Diedrich. Jack is very helpfully asking, why is Python so much more complicated than Ruby? I guess I wouldn't know. I really know next to nothing about Ruby. Every time I look at it, I get angrier and angrier. So, what I will say about CPython is that CPython as a source tree has been around for 20 years. It has been lovingly polished by brilliant men and women. It is simultaneously simple and powerful and incredibly well written. You will learn a lot if you start hacking on CPython by just reading the source code and reading the documentation, reading the comments that are in line. And it's hard to imagine CPython being better than what it is, which is a portable implementation of Python. It would be hard to make it better, to make it faster, to make it easier to read. So I really, personally, I have essentially almost no criticisms of the CPython source tree. I can't address if Ruby is any better.
So you're saying you don't know?
Yes, but in an entertaining way.
Excellent.
Thank you.
I was just curious about one thing on your last slide for the bytecode of the function. Were you returning? There's some sort of return there for returning none from the evaluation of the program of some sort?
So this is null, not none. If it returns none, then that would actually be considered a valid result.
Actually, it's the bytecode of the overall program. You're showing the bytecode for the last couple of statements.
Oh,
of the
yeah, I
overall
kind of
program?
glossed over that. Yeah, let me go back to that. I know, I meant to talk about that, and I kind of skipped it because I wasn't looking at my slides. So let's talk about the last two bytecodes here. You see this load const 1 and return value? So I'll remind you, this is the bytecode for the module. This is what you were asking about? Yes? Okay. So this is the bytecode for the module. We have a module returning a value, and actually it's returning none. I scratched my head over this when I was writing these slides. I was like, why is the module returning a value? Modules don't return values. Nobody was going to look at this number. What's it for? So it turns out we call return value at the end of any code block, because this is the way that we signal to the eval loop that it's got to stop. So we need to stop the eval loop from continuing to run. The best way to do is to return and not have anybody above us in the call stack. So if there's nobody above you in the call stack and you return, then the eval loop just stops, and we return to whoever called PIeval, eval frame ex. And return value always pops the top thing off of the stack. So this load const none, that's just grist for the mill. That gives return value something to return that's harmless. I haven't looked, but I bet nobody actually goes to look at this. Somebody said, well, it might react if that turned out to be a null value, because again, we're going to hit the bottom and deal with the housekeeping, and we might have raised an exception and that sort of thing. But in general, this is just 4 bytes at the end of every module, and it's harmless.
Speaking of the end, we are done. It is time for lunch. Thank you very much.
Thank you.